All right. So we were talking about representations of linear operators and basically its relation to matrix multiplication, right? So the bottom line is we need an identification between X as an operator and its matrix representation. So if these cats are a normal orthonormal set, orthonormal, this set is an orthonormal basis, then what we discovered so far, this is just a review, is that if you can calculate, because you assume you know what this linear operator is, so you assume you know how to calculate the matrix element, which is gotten by acting X on J and then taking the inner product with I, right? And that's the ith row, jth column of this matrix. And the operator itself can then be expressed as a sum over the cat-bra operators weighted by these matrix elements. And of course the cat itself can be obtained through a similar expression. So this is going to be a sum over the basis cats and the different ways to write this. So you can write it this way, and this alpha I, which is I, the cat alpha projected on the I basis. And so, for example, X acting on alpha, we can just write it as a sum over the cats, basis cats. But now X acting on alpha would basically I, J, alpha, J. And this is just matrix multiplication. Okay. So I don't think we've multiplied linear operators yet, so let's do that. This is just a review, and maybe I'll just write down. So for example, from this, immediately you can write down, because you know I, J, dagger is just J, I. This is a homework problem that you can prove. You can immediately write down also, you can construct what is X adjoint. Right? You can take the adjoint of X now, and this is just given by sum over Ij. But now you take the adjoint, matrix adjoint. Yeah, in other words, the matrix adjoint is related to the more abstract version of the adjoint. Okay, so like I said, I think we have not done You guys can correct me if but if I don't believe we've done multiplication of linear operators. Let me do x and y. Because I think that's what I did on notes. Let's see. Yeah, let's do that. So, actually, my notes said it yx. So let's do that. Yx. Okay. So, in fact, we can go off from what we've done here. So, we can treat yx as one operator. So we know that this has to be sum over I, and then it will be I yx, and then j. So there's a sum of I and j. So it's exactly this guy, except now x is now yx instead of x. Right? But this is one operator. But we can, because this is actually the product of two operators, we can now insert one more completeness relation. Right? So what I'm going to do is, I'm going to rearrange my numbers a little bit. So I, j, k, so it will be I, and then this last one I'm going to call k. Remember, this is just a dummy index, so I can call it whatever I want. But now I'm going to call, I'm going to insert between y and x a completeness relation. All these are completeness relations here. This is 1. This is also 1. If you sum over I and you sum over j, remember these are actually just 1, the identity, right? Something that we prove. I'm sorry, I, j. Okay. So all I've done is first I've used this result. Then I insert another completeness relation. But now you see what's happening is that just as when I apply a linear operator on a cat, it just ends up being my matrix multiplied by a column. Here, what's happening is that this is just my matrix multiplication in the sense that this is just y, I, j multiplied by x hat, j, k, k. Okay. So if you want something more explicit, we can write it out. So what is that? X, y, j, x, j, k is just the matrix 1, y, 1, all the way to 1, y, d. Remember, this is the row number. This is the row number, and the second, and then all the way to the dth row. And then this is the first column, all the way to the dth row, dth column. Okay, and then multiplied by this matrix, because I'm out of space. This matrix is multiplied by this matrix, which is, so let me just get it as a dot. Dot means this is represented by that. It's the first row, first column, all the way to first row, dth column, and then this is the dth row, first column, all the way to the dth row, dth column. Okay, so it's this matrix representation of y multiplied to this x representation of x. Right? So this is just the index notation of this guy. Or in other words, it is the IK component of this guy is this matrix multiplication over here. Okay. So essentially what you discover is for all the finite dimensional discrete vector spaces, there's a direct translation between the complex n component vector and the finite dimensional matrices into each other. Okay. And so in my notes, you'll find that basically a table at the very end of this chapter giving you the object and the translation in terms of the matrix representation. Okay, and so you should look at it if you are not familiar with this. This is the first time you're seeing this. I think I did a poll, right? Like half of you have not seen this before. So please, make sure you look at the table and make sure you can understand how that translation comes about. Okay. Any questions for me before I do the inner product of linear operators? Okay. So,
can you explain more about the multiplication between two metrics? Because when you multiply two metrics together, you got a metric.
Yes.
But in that case, you have two elements, which is bit of double complex number multiplied by each other.
These are complex numbers, yes, but there's a sum over j, right? So remember when I have a repeated index, there's a sum over j. So this is in fact the y matrix times the x matrix, and this is the ik component, as I said over here. And this sum over j represents that matrix multiplication. Is that answering your question? So I'm just writing out explicitly what you would do, but this is what I mean. But you're right that, of course, if you fix I, j, and k, these are just numbers, of course, right? But there's an implicit sum over j, which corresponds to matrix multiplication. Yeah. Okay. So let me say the next thing then, if there are no other questions. Let me put it in the context of linear, the finite dimensional case, because it's easy to see. Right? So let me write it as the following. Linear operators themselves form a vector space. Right? And so the easiest way to see is that you have in fact proven in your homework, which I think is due today, is that right? Or last week. That matrices form a vector space. Right? And you have just seen, I won't prove it for the continuous case, but so for finite dimensional vector spaces, linear operators are matrices, and these matrices form of vector spaces. Okay. can be identified, right? That's a better way to say can be identified or represented. And matrices form a vector space. And therefore, the linear operators themselves can be seen to form a vector space. At least when the linear operators act on the same space to give you vectors in the same space. Sometimes, I should just say it as an aside, right? Usually we don't do it because we're doing quantum mechanics. But sometimes your vectors, your linear operators act on one space, but as an output gives you vectors in a different space. And in that case, it's actually going to be one of your homework problems. In that case, the dimensions could be different. The dimension of the input vector space could be different from the dimension of the output vector space. And in that case, you won't have a square matrix anymore. So the fact that these guys are square matrices, these are D by D matrices, is because the input vector space is the same as the output vector space. So for your homework, you figure out what happens in the situation where you are not acting when the input and output are not the same. Okay? But at least for most of our problems in quantum mechanics, you are acting on the same space as you are outputting. So this will be the situation. But even in that case, the linear operators will still be a vector space, even in the case where the input and output are not the same. But the caveat is that what I'm about to do, which is to define the inner product, may not work anymore. Okay, so this is always true. But the inner product, because when we do quantum mechanics, usually we want to do inner products. And that oftentimes don't work anymore because they're not square matrices. May not work as well, at least. Okay, so how do you take the inner product? If linear operators form a vector space, meaning they are vectors in their own space, which is to be distinguished from the vector space they're acting on, right? So this is now a vector. But of course, this is not a vector in this space, right? So they form their own space. How do you think about taking the inner product? So it turns out that this is related to the trace, which you also prove for the matrix case, right? So here I'm just going to write it down for the linear operator case. So the inner product between two linear operators, so these are now linear operators. How do you do that? You define it to be the trace of x dagger y. Well, what does that mean? So this in turn means that you sum it over, you sum this guy over an orthonormal basis. So these guys is orthonormal basis. So in fact, let me just say that one more time. So the trace doesn't have to be, it doesn't have to be involving two operators. The trace of any operator is given by this definition. It's a sum of the diagonal, this is basically the diagonal matrix element, is the II component of A, summed over all the diagonal components. So it's basically A hat I, basically. Now you might wonder if you if you know some geometry, especially, or if you think about it physically, choosing an orthonormal basis is like choosing a coordinate system, right? And this is something that I'll come back to again, because it's something to do with symmetry. So if you choose an orthonormal basis, for example, let's think about it in terms of real space, right? If I choose this with x, this with y, this is z, it's a choice that I make, usually based on the problem that I want to solve, and usually it's tailored so that I can solve the problem easily. But it's a human construct, right? I choose my coordinate system. It should not matter whether I solve the problem using x, y, z like that, or I rotate my axis a little bit, or I tilt it a little bit like that. It might be harder to solve in a practical sense, but it should not change the underlying physics, right? So why am I saying all this? Because if I take the trace with respect to some orthonormal basis, you should question, is this something that will change, if the answer will change, if I switch to a different orthonormal basis, right? This is something that you should ask. And the answer is no. In fact, we will show later on that this number, right, the trace is a number, because you're taking the diagonal components of this operator, and then you're summing over all of them. So this number will not change, no matter how I choose my orthonormal basis. As long as the orthonormal, I claim you'll get the same answer. Okay. So let's do an example of trace. So for example, let me define an operator that is just I, j. So I and j are fixed, but I just choose a cat and a bra where I and j need not be equal. They can be equal, but need not be. So let's, for example, think about how to take the trace of x. Okay. So the trace of x, actually let's do this, and then let me take y, and then I will choose another set, let's say m and n. Okay. And I want to show you basically because these guys are orthonormal, as I've assumed, in some sense they are orthogonal, this kind of operators are orthonormal. Okay, so how do I show that? So x inner product with y is the trace of x dagger y. And first let's work that out. So x dagger, remember, is y, I, j, dagger, and then acting on m, n. Well, in your homework you've shown that I, j, dagger is just j, I. And now it's acting on m, n. Okay, so before I even do any trace, I know that I have a Kronecker IM. Okay, this is Kronecker IM. Why? Because if I is not equal to m, is 0, right? I'm assuming I have an orthonormal set. So I and m are orthonormal. and I get a Kronecker IN. And then I need to do Jn, so trace of Jn. And this is where I need to plug in the definition over there, Kronecker IM, and now I need to sum over, let's say L of Jn. Well, what is that? So what you notice is the following. So you have to reason a little bit. If J is not equals to L, is 0. But if N is not equals to L, is also 0. So that means that J and N better be equal. Because if they're not equal, there will not be any L that is simultaneously equal to J and N, right? So what you discover is that J and N better be equal, otherwise it'll be 0. So I put a Kronecker delta here, but there could be something here. So let's think about it. Now let's say J and N are equal. Okay, so let's say J and N are equal and is equal to some number. Let's call it X. But this is a sum over everybody, right? So this is now a sum over everybody. And so if, as long as J equals to N equals to some number, you will sum over a set of numbers that will include S, which means there will be some S, which is just 1. So that's the answer. Okay. So everybody is 0 except when L equals to J equals to N, and that term is 1. Right? And so, as I've claimed, there's some kind of orthonormality between these sort of bracket operators. Unless I equals to M and J equals to N, right? So the cats have to be equal and the bras have to be equal. Otherwise, the operators are orthogonal. Yeah, perpendicular. Okay. And of course, you can also, if you have a more complicated operator, let's say you have A, B, and you want to take that in the product, then the more usual way you end up doing it is to write it as a matrix operation. Okay, so what is that? So remember, this is now just sum over K, A, J, B, K. Sum over K and J. And, oops, I'm sorry, there's a dagger here. So remember, the dagger just means transpose complex conjugate. So it's really J, A, complex conjugate K, and J, B, K, sum over J and K, and in matrix notation this would be A hat J, K star or complex conjugate, and then A, oops, I'm sorry, B, J, K. Okay. Or if you want, you can just write it as a dagger of K, J, B, hat. Okay. All right. So, there are no questions. I'm going to move on to the next topic. Right. So for the next probably week or so, maybe a bit longer, I'm going to start to talk about two special kinds of operators. One is a Hermitian operator, and one is a unitary operator. And the reason why we spend time focusing on it is because they play a special role in quantum theory. So, so we'll start with Hermitian operators. And so let me just remind you guys, so we're doing linear algebra because quantum systems are basically described by vector spaces. Now, for Hermitian operators, this is the second postulate of quantum mechanics, which is that most observables in quantum mechanics correspond to Hermitian operators. And as we will see, the reason why that's the case is because the eigenvalues of Hermitian operators are guaranteed to be real. Okay, so let's start that. What is a Hermitian operator? X is Hermitian if x dagger equals to x. Right, so in other words, the self-adjoint. That's what mathematicians like to say. Right, so if you take the dagger, you get back itself. And there are many ways of writing it, but you can write it in terms of matrix elements, for example, alpha, beta. Remember, if you take the complex conjugate, the rule is that you have beta, x dagger, alpha, right? Because you can think of this as basically this is the cat, and you're going to take the adjoint, and then this bra becomes the cat. But because it's Hermitian, this is just beta x alpha. Right. So if alpha x beta complex conjugate is equals to beta x alpha for any alpha and beta, then your operator is Hermitian. That's another way to define. That's another way to define Hermicity. Okay. So the first important fact is that Hermitian operators have real spectra. Real spectra. Spectra just means the set of eigenvalues. Okay, so this is just a set of eigenvalues. let's prove it because it's pretty easy. Okay, so suppose A is an eigenvector of x. So when I apply x on A, that means I get A. Okay, remember that we are going to, if a linear operator has an eigenvalue, we're going to label its eigenvector with its eigenvalue. Okay, and so if I have, let's say, A prime, then this will give me A prime. So I can certainly take the adjoint, right? And because it's Hermitian, by assumption, this will become A prime x equals to A prime star A prime. Right? Remember, the rule is that when you take the adjoint of a complex number times a ket, you get the complex number conjugated times the prime. Okay. So now I can do a few things. I can multiply to the left by A prime here. So I can do A prime x A equals to A prime A. Okay. And from here, I can multiply to the right the ket A. So I get A prime x A is equals to A prime star A prime A. Okay. So the left-hand side are equal, right? So we're taking the matrix element of x with respect to the eigenvectors of x. And what we find is the right-hand side looks a little bit different, but I can subtract them, right? So when I subtract them, I get 0 equals to A minus A prime star times A prime. Oops, I'm sorry, A prime A. So what do I discover? So suppose there are a few possibilities, two possibilities. Suppose A is not equals to A prime. Okay? So then actually let's say suppose A equals to A prime. Okay. Then let's start there first because we need to prove this fact first. So then what we have is that we have 0 equals to A minus A star times A. Right? I can put A prime as well, but they're the same. So I can write A prime minus A prime star A prime A prime. Okay. So remember that I'm assuming it's an eigenvector. So this is not 0. It's not a 0 vector. So this cannot be 0. This is not 0. This is not 0. Okay? And so if this is not 0, that means that A must be equal to A star. Because this is not 0. When you have two things multiplied together, it gives you 0. So the only thing that can happen here is that A equals to A star, which means what? Which means A must be real. Okay, so I've proven this fact. Okay, it cannot be anything else but real. You have a question? Yes.
Should be A from star.
This one? This one? This is A prime star. Yeah.
Last one.
This one? This is a bar.
Oh.
Yeah, bar. Sometimes I use a bar, sometimes I use a star. Yeah, which is the same thing, right? So bar is the same as star. A bar equals to A star. Okay? It just depends on whether which one is easier to write. But yeah, I use both. You will see both in. Oh, I should also say, you will see both in math. And maybe I'll also say, in math, sometimes in the math literature, sometimes you see A star to actually mean A dagger. So this is math. In physics, from what I can tell, we always use dagger. Right? But sometimes you see A star. So be careful. Read the book first. They will usually define for you that notation. Usually there's a page of notation. Yeah. Okay.
So how do you write off that?
Huh?
First, 0 equal to A minus A. So,
This?
yeah.
What do you mean?
How did you write off this?
How did I write down this? From here, right? From here. You mean how did I get here? You mean how did I get from here? So I'm considering two cases, right? A equals to A prime.
Oh,
And then next time, the next case will be
okay.
A not equals to A prime,
Okay.
right? Yeah. So you understand how we got here, right? And so the first case is when A equals to A prime. And that proves that all the eigenvalues of X must be real. But we didn't assume anything about X, right? X is just permission. So therefore, all eigenvalues of X must be real. Okay. Now, if it's not the same, then we can come over here and we say, we come back to here and we say the following. Now we know that all the eigenvalues will be real, so now I can take out the star here because it's real. So I get 0 equals to A minus A prime A. And these guys are real now, right? These are real because I've just shown it. I've just shown that everybody is real. So, and furthermore, the difference of this, because I'm assuming they are not the same, cannot be 0. Right? So A minus A prime is not 0, which means I can divide both sides by it, and I get 0 equals to A prime A. That means that, what does that mean? It means that not only are the eigenvalues real, eigenvectors corresponding to different eigenvalues are orthogonal. So eigenvectors of Hermitian operators corresponding to different eigenvalues are orthogonal. Okay. So maybe I should say fact 1 and fact 2. Okay, so this is fact 1. And this is fact 2. So they are very important because it tells you the following. When you have a permission operator, as we'll see in quantum mechanics, they tell you they tell you the range of possibilities that you can get when you make a measurement corresponding to that observable. So maybe it's spin, maybe it's position, maybe it's energy. Energy is the most frequent observable that we'll talk about when you talk about atomic spectrum. What it tells you is the range of possible outcomes that you can get. Right? So this is the Born rule. You can't get anything else except the eigenvalue of the observable that you are trying to measure. Right? So if H is the Hamiltonian, if X is the Hamiltonian, then its eigenvalues will determine the possible energies that you can get. But so the fact 1 is important because it tells you that when you measure something, it should be real, right? There's a length or there's an energy, observables that you can read from your instrument should be real. There's a number, right? So that's the first important reason why we care about permission operators. The second important reason is that if you have different outcomes, if your measurement can give you different outcomes, then these states, the range of possible states are also orthogonal. So, and we also know that orthogonality implies linear independence, right? So they form, as you will see, in fact, the possible states labeled by different eigenvalues form basically a good orthonormal basis for your system. That's the reason why this is important. And in fact, that's the next statement I'm going to make. Something I'll write down as fact 3. The eigen vectors of a permission operator span the vector space. So what it means is that you can use the eigenstates to describe the whole system. You can fully capture the system itself because it forms a good basis, right? And so let's write that down. In fact, in terms of a completeness relation. Right? So for example, if you have x lambda k, in my notes I call it lambda k because I have to label my eigenvalues. So then you find that because of this theorem, the identity operator, so completeness, is just the sum over all the eigen projection operators. Okay, sum over all the eigencaps, or the eigencadra operators is complete. And this is very important. Again, So this is why in quantum mechanics, this is why it's important to know your observables. Okay, because not only do they determine the outcome of possible experiments, but if I'm measuring spin or momentum or energy, they also determine the entire space, where the observable itself, the eigenvectors, parametrize the entire space. I should mention at this point, because we're talking about eigenvalues and eigenvectors, the notion of degeneracy. Right? So this is a little bit tricky to talk about at this point, but degeneracy just means that you have the possibility of repeated eigenvalues. And so there can be an ambiguity when you label the eigenvectors here. But in physics terms, I should mention that if your observable has a degeneracy, then it often indicates that there is a symmetry, there's an underlying symmetry in your problem. So let me say that, let me write it down in words so you see. Degeneracy. So what is degeneracy? Is the possibility of getting a spectrum is degenerate if there are repeated eigenvalues. So the simplest example is we can just write down a diagonal matrix, say 1, 1, 2, 0, 0, 0, 0, 0, 0. Okay, so that's simple enough. The eigenvectors are 1, 0, 0. We'll give you back 1, 0, 0. If you acted on 0, 1, 0, it will also give you back 0, 1, 0. So you see that the eigenvalue here is 1. The eigenvalue here is also 1. And only when you acted on 0, 0, 1, then you get twice 0, 0, 1. Right, so here that is 2. So that's a simple example where you have a repeated lambda of 1, and that's a degenerate case. This is just a math example, but the physics of this is the following. Later we will see that when there's a symmetry in the problem, degeneracy, you will get a degenerate spectrum. Okay. The other way is not so clear to me. I think people suspect that usually is the case, but I don't know whether you can prove the other way around, whether degeneracy implies symmetry. But you should certainly think about that. If you ever have a quantum system either whether you are a theorist or experimentalist, if you ever find that your spectrum of some observable turns out to be degenerate, then I suggest thinking about symmetry. There could be an underlying symmetry that you are not aware of. You may have forgotten about it, or maybe you're just not aware of it. Right? Again, symmetry definitely implies degeneracy, but the other way around, degeneracy, I don't know whether it always implies symmetry, but it's something that, as physicists, we should keep in mind. Okay, so I think we should take a 10-minute break and come back. Okay. Any questions for me? Yes.
So can we prove the vector 3 with the abstract Hermitian operator?
Yeah. So So I should have said I will not prove it in general, but for finite dimensional, I should write this down. Yes, that was a good question. So how do you show this? So fact 3 is basically just the same as saying that all Hermitian matrices are diagonalizable. Yeah, so again, if you give me a Hermitian operator, first I can calculate a matrix element, because I assume I know what the linear operator is. So choose an orthonormal basis, compute its matrix element, diagonalize the Hermitian matrix as though you are diagonalizing, just as you would diagonalize a Hermitian matrix. Then you will get it in terms of U times the eigenvalues times U dagger, where U are the columns formed from the columns of the eigenvectors. And then what you discover is that the cat, eigencat itself, is just a superposition of the original orthonormal basis that you have chosen, summed over the row of the U of your basically your eigenvectors in this matrix representation. Okay. So in your homework, I believe you have some simple examples that you can practice on. And that, in turn, answers your question, which is how do you prove factoring, right? Which is that you're guaranteed that if you have a Hermitian operator, your eigenvectors will always span the space. Why is that so? Because you're guaranteed with H is Hermitian, you can always find a unitary matrix that can diagonalize your H. And because it's unitary, you know that you have you have a set of orthonormal bases that spans your whole space. That's the proof of the statement, at least for the situation where you have finite dimensional vector space. Right? It's much more complicated when you have continuous operators. Then you'll be dealing with very often partial differential equations. But we'll get to that in a bit. But we won't prove that statement in that case. It's a whole discussion of functional analysis in math. But at least the finite dimensional case is, I hope, good motivation for you to believe that it holds in general. Okay, so like I said, in quantum mechanics, it's very important to identify your observables. Firstly, because it gives you the range of possible outcomes in your experiment. Right? So maybe I should write that down explicitly. So these are some of the important facts so far that we have learned. That the outcomes are determined by the eigenvalues, and the eigenvectors themselves, they span the vector space that you are studying, because that corresponds to the quantum system. But which observables are important? That's the question. Right? So it turns out that you cannot use, there's an issue of compatibility, which we are now going to talk about. So what do we mean? So X and Y are said to be compatible if they're commutative. So we're going to define this bracket, which is called the commutator. And the commutator between X and Y is just X times Y minus Y times X. Okay. So why this is an important concept is because, like I said, we need to choose an observable to use as a way to parameterize, to describe our system. And so the key point here is that X and Y, maybe fact 4, are simultaneously diagonalizable if and only if they are compatible. Okay. So what does it mean to be simultaneously diagonalizable? Simultaneously diagonalizable. It means that they share the same eigenstates. Okay, so means X, Y share the same eigenstate. They may not share the same eigenvalues, but they share the same eigenstate. So for example, if they are sharing the same eigenstate, I will have now two labels. One label for the eigenvalue of X, and one label for the eigenvalue of 1. But the same state is both an eigenstate of X and an eigenstate of 1. Right? So this is what it means to be simultaneously diagonalizable. But like I said, it's not always possible. Okay? It's possible if and only if they are compatible, meaning only if and only if they commute. Okay, this is very important. So that means that if you have a quantum system, you try to maximize the number of observables that you have in your system. But you can't have too many, in the sense that some of them will not mutually commute. They are not compatible. And if they're not compatible, then you cannot use them as simultaneous observables. Okay, so that's the key point. And especially later on, we're going to talk about atomic spectra, and you're going to talk about addition of angular momentum, and this starts becoming a bit more tricky. It can get a little bit confusing. So it's always important to keep this in mind, this basic but very important fact that they're simultaneously diagonalizable if and only if they commute. Okay. So let's try to prove that. And then that's probably it. So they're both, there are two ways, right? So let's do the easy one first, okay? They're simultaneously, if X and Y are simultaneously diagonalizable, then they commute. Let's prove this statement. Okay? Well, if X and Y are simultaneously diagonalizable, that means, as I've said over here, they share the same state. And we have shown previously that in a diagonal form, X just takes A, B, sum over all the eigenvalues of X, all the eigenstates. Okay? And Y, likewise, will be B, AB, B. The sum over all the eigenstates of one, but they are the same state, right? It's just the eigenvalues are different. So now all we have to do is just commute them. Just compute the commutator. So what does it look like? You have a sum over A and B. And first you have this guy applied to that, but got to be a little bit careful here. So because I'm summing over two sets of projection operators. So what I'm going to do is I'm going to call them A prime, B prime, and A, B. Okay, so X will be this A prime, A prime, B prime, A prime, B prime. This is X acting on Y, which will be B, A, B, A, B. Okay? Minus YX. So it will be B, AB, AB acting on X, which is A prime, B prime, A prime, B prime. Okay, again, this is X acting on Y, and this is Y acting on X. The reason the reason why there's a prime and there's an unprime is just because I need to distinguish between the summation over for X and the summation for Y. Okay. But they're all dummy variables. So this is where you recognize when this X on this guy, remember that these are orthonormal. Okay? These are orthonormal. And so when they act on each other, it will be 0 unless they're the same. Okay? Again, when A prime, B prime acts on AB, it will be 0 unless they're both the same. Which means that this double summation will collapse into one summation. So what will you, and then A will become A prime. So you get A times B, and then I get A, B. Remember this has collapsed into AB. So let me just say it here. Right. So A prime, B prime, AB is 0 unless A equals to A prime and B equals to B prime. And that's why you get AB, AB, AB for this, minus, same thing here. AB acting on A prime, B prime is 0 unless A equals to A prime and B equals to B prime. And so, again, you get B times A, and then you get A, B, A, B. Which of course is the same thing, which is telling you that it's 0. Essentially what you discover is that this is just a complicated way of writing the product of two diagonal matrices. That's all we're doing. We're just multiplying two diagonal matrices together, and because diagonal matrices commute, therefore the commutator is 0. Okay? Let's see. Okay, let's finish the proof, okay, and then we can continue next time. So let's show that if x, y is 0, then x and y are simultaneously diagonalizable. By the way, this is what, in case it's not clear to some people, this is what if and only if means. And very often I'll use shorthand. I'll just write it as I at F. It just means if this is true, then this is true. And if this is true, then this is true, right? A if and only if B means A implies B and B implies A. Okay. So that's why we have to do it in both directions, the proof. So the way to prove this is we start with X. Okay, X is formation. So we know that is expandable in terms of its eigencaps, like that. Right? So this is guaranteed because it's Hermitian. So now we're going to assume the xy is compatible. So what we can do is we're going to compute a prime commutator of xy a, okay, in this basis where x is diagonal. So what we know that this is 0 because we assume the commutator is 0. Okay, but what does that mean? It means that a prime xy minus yx a, and x can act on x a prime, so you get a prime y a. Okay, again, x acting on the left is Hermitian, right? So this guy is your a prime y a. This guy now have a prime y, x acting on a will give you 8. Okay, so in other words, I have now a prime minus a times the matrix element of y with respect to a prime a. They are arbitrary, the eigenvalues, eigenstates of x, but otherwise completely arbitrary. Okay? So, but it's 0. So again, if a not equals to a prime, in other words, they don't refer to the same state, then we find that a prime y a is 0. That means what? That means that if you view this as a matrix, there's all the off-diagonal terms are 0. Right? But that's it. So that means that the only non-zero terms are only the diagonal terms are non-zero. Okay. And that means in turn that we have diagonalized y as well. Right? So in other words, once you have diagonalized x, that means you have also diagonalized y, because we have assumed the commutator is 0. So we have proved this theorem. Right? So again, the spirit of this theorem is that you want to choose the maximal set of operators in your quantum system that commute with each other to fully characterize your quantum system. So let me just write it down. The quantum mechanics, we want to choose the maximal set of compatible observables to fully characterize the system. If you have more than that, they don't commute, and you cannot simultaneously diagonalize them. But if you have too few, then you're missing something, right? So even though all the eigenclass span the space, you might be missing some information about spin, or missing some information about momentum, or something like that, right? But so So this theorem tells you, you cannot go too far, too many, but for physical reasons, you don't want to go too few as well. Any questions?